Hello everybody and welcome to our next tutorial. Today we're going to talk about really special phenomena. Why so? Because we finished to talk about electricity. Okay, we're done with that, and then we continue to magnetism, the magnet, and we also finished to talk about that in the last tutorial, which was about inductors. And right now we heading to our final subject, which is waves. And right now we're going to start in some introductions about waves. Specifically today, let me adjust the zoom. Specifically today, we're going to deal with two subjects. First of all, we're going to deal with a string. And for those of you that already know me, what a really good example for a string, it's a guitar. So we're going to talk a little bit about guitar today. And also we're going to talk about waves in the sea. Okay, so this is the two subjects for today. So let's heading on to the subject. So as you can see, I have here my guitar, and when you look at the guitar, you see this string, this nice line that start over here. It cannot move at that point, it's locked at that point, and it's continue to this point. So these 2 points cannot move. I want you to remember that part about the physics of the guitar. So let's continue. Let's draw the question that we have. I'm gonna clean this one up. So let's draw some guitar. So here's the guitar, the body of the guitar. And here I have, if this is the body, we have the neck. And the top of the guitar we have the head of the guitar. So this is a general look of a guitar. And here I have maybe this hole, right? And we said that the guitar have strings. I'm gonna draw only one string, but the idea is similar to the other strings, okay? So the string is actually, look here, right? It's holding here. You have here some, I don't know, some key to take up the tension, but the string cannot move at that point. And then the string is a straight line till this part, and the string cannot move at these 2 points. And there's a given data in the question. The given data is the length of the string is given. It's less than a meter. It's 0.85 meters. And also I know the mass of the spring. The mass of the spring is 0.03 gram. It's really easy to lift. Okay. So this is the parameters that, the given data that we have. And the first question that we're gonna deal with is what are the different mode that this string can vibrate, okay? How, if I'm gonna look at the spring, how it's gonna look like, how it's gonna react. So let's try to do it. So the basic thing, okay, to see this point, how this string is moving. So the basic thing that I can think of is to take the string, right? It cannot move at my elbows, right? So I'm gonna have this kind of motion. This is like going up, going down. This is the simplest idea that I can think of, okay? So I don't know if you remember in the lecture you saw about waves, that if you drawing a wave, so if you take some random point and another the same point after a period, so this distance is signed as lambda, okay? So this is the wavelength, lambda, and if I'm looking at a string in the, let's delete the given data, let's clean it up a little bit. So if I look at this configuration, going up and then in the next part is going down. So if I think about that, this is actually half of lambda, right? Because if it's gonna continue to be more sinusoidal wave, right? So this is gonna be half of a full circle. So lambda is actually 2 guitars, okay? So lambda in this configuration, let's call it configuration 1, okay, 1. So lambda is actually equal to what? Lambda 1 equal to 2L, 2 guitars, okay? Another configuration, if I want to complicate it, let's say that the string cannot move also at the middle. If the string cannot move at the middle, So we actually divided this problem to two problems, right? So let's do it in a different color, so it's gonna be easier to see. It is, oh, this is good red. So I'm thinking about this configuration. What is this configuration? It's the same idea. This part do the same thing. And the second part, this one, do the same thing. Okay, so we actually have like up, down, down, up, up, down, down, up, up, down, down, up. That's the configuration we have here. And this case is really simple. Okay, case 2. Case 2. Why it's simple? You know what? Let's call it n equal to. Okay, we're gonna say what is n in a second. Maybe some of you remember from the lecture, but let's call it n. n1 and n2. So n2, you see this configuration, is actually equal to the guitar itself, to the length of the string, right? So this is lambda. So you see where I'm going. Let's do a more complicated variation of that idea. So let's do 2 points that cannot move. So let's do here and here, at the first third and the second third. So I'm gonna have kind of hop, hop, hop. So what I'm gonna see here, it's more complicated to do it with the hands, but this part's going up and down, and this one go up and down, and this one go up and down, up and down. So this configuration n equal 3. Okay, and what is actually lambda right now? From that point to that point is lambda 3, right? Equal to what? To 3 over 2 L, right? Right now you see that to do that if this is the length, so I want, sorry, wait a second. I think it's the opposite. I think it's 2 over 3, sorry. Don't know why I wrote it the other way. 2 over 3, right? That's what we have here, right? At that location, this is the lambda. See, third and third, 2, and we left with another third. So now I want to talk a little bit about this n. Okay, what is this n? Okay, so the places that the guitar cannot move, for example, the start and the beginning, here it is. The start here, it's called the bridge, this part. And at the head of the guitar here, cannot move, called notes, okay? Notes. So notes is the place the guitar is not moving. So this place is called notes. Notes, okay? Not moving, okay? At all. So what's the idea here? So I remember it is, I asked the string, do you move at that location? And it notes, okay? No, okay? Notes, no. So that's how I remember it. And the places that the string is moving the most, right? The extra move, this peak move the most, it's go from the top to the bottom, right? So this place is called the antinodes. Okay, I want you to remember this. And the antinode is actually this n. Is the question how many antinodes does the string have in this vibration? Okay, that's the idea. So I can see that for one mode, for only one extra move, one maximum and minima, right? So lambda equal to L, okay? And for, let's do it in red, and for lambda equal 2, when I have 2 extra moves, the red one, 1 and 2, right? So it's equal to L. And lambda 3, when I have 3 extra moves, 1, 2, 3, right? I have this one. And if I would continue going with this idea, I will find myself, what? Have lambda of any mode that I want and any number of antinodes in the string actually equal to what? To 2L over the antinodes. Antinodes, the number of extra move and minimum that you have on the string. Okay? So this is all the configurations, okay, that the string can move. Okay, if you look at the string, this is the configuration it's gonna move. Okay, perfect. So let's continue on to the next question. So actually, when you're looking at the guitar, it's combination of all these solutions, okay? In the lecture, you solved the equation and you saw that this is the result. This is the only possible option for the string guitar to move, and all the options are the specific option that you look at the guitar. It's some combination of all of these modes, okay? Modes, the way that I can appear. So this mode and this mode and this mode, okay? So that's the idea. Let's move on to the next question, which is more interesting. I'm gonna clean the board. Here it is. Okay, so the next question is, what are the frequencies that the string can vibrate? Okay, the string is vibrating. You see this motion, up, down, up, it's vibration, okay? So I want to ask, what are the possible vibrations? So you solve the wave equation and you got to this solution. Solution is the velocity of the phenomena of the wave equal to lambda multiplied by f. Okay? So what is V? V is it's the disturbance that propagate. What is wave? Wave is some problem, something that happened, okay? Something happens, something move, and it's going through some medium. That's the idea of waves. If I do splash in the water jump, right? And it's moving, it's propagating inside the water. If I'm shouting at you, right? I actually introduce some pulse of energy, and it's moved through the medium of air until you get to this microphone, okay? That's the idea. That's what wave is all about. So this is the velocity of the propagation, the phenomena, right? The propagation of the energy that I put in the medium. This tell me how it's look like, right? This is the wavelength. We talked about it, how it's look like, okay? And F is the frequency. What is the frequency? It's vibrating. Okay, so these two related to each other, okay? So how I can find what is the frequency? So I just can use this term and put it inside here. And that's it. That's how I can find the frequency. So the frequency, and something really special gonna happen, equal to what? To V divided by lambda. So V divided by lambda. But we say that lambda is a function of how many extra moves do I have? And I want to remind you just that we're dealing with standing wave. This equation only holds for standing wave. And I want to say what is standing wave. Standing wave gives us the illusion that the string is actually staying, like the phenomena, the propagation, the energy that going inside the string is like staying in place. That's a feeling, but it's just an illusion, okay? So, but that's how it look like. What I mean by saying that, you see the propagation, the energy is going through the string, okay? Something going on. And it gives us the impression that this point, okay, this point does not move. So it makes you feel like the string is staying in place. That's the idea. So if I have this phenomena, hop, 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 or this one, right? This is the second mode, right? Second one. So it looks like this point doesn't have any energy, right? That's how it looks like. Okay, because it's staying in place. It looks like the string is staying in place. The phenomena is staying in place, so it's called standing wave. Wave that stays in place. So that's the idea. So, so I use the equation for standing wave, put it here, and what I get V over 2L multiplied by N. And look, something really interesting happened. So as we have specific wavelength for each antinode that we want to look at, each case, so we actually have also F as a function of N. You see it? And what's also cool, so see that this N, if it's equal to 1, this is F1, right? So we actually, F is it's a multiply of F1. This is Fn. So this is another important equation for standing waves. Okay, you see this one? You see this one? Two important equations. Okay, perfect. And F1 equal to what? To this. To V divided by twice the length of the string. Perfect. Okay, we find that. And and I want to say something about musical instruments. Okay, let's clean the board just to give you something to understand how our world is working. So I think it's really interesting. That's the reason I'm telling you that. So if you look at here it is, and if you look at some instruments, okay, and you look at the frequencies, okay, this is F1. If I'm gonna double it, it's gonna be F2, which is twice this one, right? 2F2, and this is F3, which is 3 times. Sorry, this is one. F1, F1, and so on. And if I look at how much the sound, if I look at the sound, okay, the sound that I'm hearing, okay, if I analyze the sound, I look from which frequencies this sound's made of. If I see a picture like this, not much, boom, wow, this mode is vibrating really hard. And then I see another phenomena, boom, wow, this mode is not intense like this one, but it's really strong. And boom, wow, F3 is like F1. So if I see that only these frequencies are really intense in the sound of what I'm hearing, it means that I actually using a musical instrument, okay? That's the idea. So this, for example, is a guitar, and a violin maybe gonna look like this. This peak gonna go until here, this one gonna be the dominant one, and this one gonna be small, and this one gonna be huge. Okay, so this is like the idea of the instrument. So this can be a guitar string, this can be also maybe a harp, maybe many things, even a drum, or many stuff like that. Okay, any musical instrument that you hear is actually it's dominate in those frequencies. And just a head up, these ones are actually called harmonics. If you are a musician, it's good for you also, harmonics. And how it look, the graph for something that is not that musical. Okay, for example, the drum kit is not that part of the drum kit are musical, but think about it, they don't have a specific note, right? So when I need to think about chords when I play the guitar, but the drummer need to think about the rhythm, which is a different art, okay? It's not the chords and the harmony and stuff like that. Why? Because when I look at the graph of for example, the board, okay? For what sounds these frequencies built of? So if I look at the frequency, this is the sound, for example. So actually, the intensity of the sound, I'm gonna say something not clear. You see it? There's no specific peaks in those frequencies. There are no specific frequencies that dominate. So that's the idea of drums, okay? The kick, the kick. You have the kick in the drum, right? The bass drum, and you have the snare, right? And you have many other tools that you can use, okay? But that's the idea, okay? This is just to give you a heads up, like what's going on in a musical phenomena. Let's go back to the guitar and our problem, okay? For me, it was really important to say that, so you would know it. So let's move on. So I leave this one is important, this one is not important anymore. Okay, so the next question is my string, can tear up, okay? That can happen, we know that. We know that when somebody play guitar, string can pluck, right? It can happen. So I want to ask you, if I want to play the frequency F1 is equal to, let's do 110 Hertz. I want to play this one, okay? And this specific one is actually the note La, A. This is the note A, which means La, okay? For the musician here, maybe it's helpful. So what does it mean? I want the string to vibrate in 110 per second. Hertz, it means per second, 1/second. Which means that the string is gonna slap the air in this frequency. In each second, it's gonna slap the air 110 times. It's insane, okay? So this is the frequency A, okay? And this actually is a low frequency. There's even higher frequencies, more intense frequencies, okay, really fast. Okay, so that's the idea. That's how I want you to think about that. So I tune the string to be in this frequency, and I want to ask, what is the tension? What is the tension, and I'm gonna note it as T node, okay? Node, because I don't want you to confuse with the time period, right? So T node, what is the tension of the string, okay? The tension of the string. So to find the tension, I want you to go back to the equation of the frequency, okay? So Fn, okay? And let's say no, never mind. Okay, so Fn is equal to n multiply V over 2L. Okay, so L is given, right? Was given at the beginning. We talk about it 0.85. And n is given. They say they want to talk about the n mode, and n equal 1, which means I know the antinodes. Okay, perfect. But I don't know the velocity, right? We don't know the velocity. For that, I'm going to give you another equation, which is really important for standing waves, and specifically in string. Okay, this equation valid to, it's more narrow. Okay, we start with standing wave, and then we talked about string. Okay, now it's more specific. Now okay, so for string, I can say this thing. Look at V, okay? Not look at me, look at V. So V actually equal to the square root of the tension divided by the mass density, okay? So what is each term here? Okay, so this is the tension of the string, okay? For example, you see this guitar, I have these keys, and these keys actually pulling the string, push it more like a rubber, that I push it more and more and more. That's the idea, okay? So this is actually the tension. But what's also really important, which kind of spring that I try, you know, to coil up, right? I try to pull it up. So this is this mu. The unit of mu is our kilogram per meter, okay? It's the density of the string. How heavy is the string? So I can talk about many length of string, okay? 2 kilometer string gonna be really different from really small string. So this is normalized by the length, okay? So if I want to find mu, look at the unit, I understand, okay, mu is actually how much, what is, this is unit, how much, what is the weight, and here is meter, here is mass. Okay, how much weight per how much length, right? So we know both of them, right? We talked this is 0.03, right? And we talked about that the length is actually 0.85 meters, right? And this is kilogram, right? So that's what we talked about before. So now I have everything that I needed, right? I can delete this one. I have everything that I needed for these terms. So I actually, let's change the red, because the red is really strong in the eye. Alright, so I can rearrange the equation, right? And I'm gonna get the T node, equal to 4 times F1 square, right? Multiply by L, multiply by M. Okay, this is what I'm getting if I'm gonna rearrange. And if I'm gonna put all the result inside, I'm gonna get a really nice number that go 1, 2, 3, and 4, right, newtons. And the string gonna tear up at 2000. I didn't say at the beginning. Okay, sorry about that. So I can see, I can be sure that what? It's not gonna tear up. It's not gonna happen. I want also to write this equation here. So we see that the frequency of a string, this thing is specifically to a string. I want to emphasize that, okay? If we're gonna do some movement of wave in a water pool, so that will not be valid because there's no talking about tension. It's water, right? There's no talking about mass density, maybe it, but not per unit of length, right? It's not make sense when you talked about water. So this one not gonna be relevant when you talked about water. You should do this, you know, should do this kind of way of thinking. Okay, this is not relevant. But frequency is actually what F1 is called the basic frequency, okay? The root frequency is the most important one, okay? The fundamental, this is the word that I was looking for. Fundamental, okay, frequency. Why? Because all the other frequency building up on this, it's just multiplication of this one, okay? So this is important. F1 equal to what? We said it's 1, this n is actually 1. V is actually T over mu, the mass density, right? And divided by 2L, okay? So if I taking my guitar and I'm gonna change the length or the tension, right? Or the string that I'm choosing to play, I'm gonna have another frequency, okay? It's another instrument. It's important to say it, okay? For example, let's take the guitar. So you see something really nice about guitar. So guitar is actually what I do when I play, actually all the time changing the length. Look at that. So the length of the guitar is from this point to this point. But if I'm holding, this is the note, you hurry. But if I gonna press at this point, you see, not here when it's naturally pressed, I'm gonna press here, I'm gonna short the string. It's gonna be super short, okay? So you see it, it's really high, really low, really high, okay? What I did, change the length. So guitar players actually changing the length of the guitar. And another cool thing that I can do, okay, I can also change the tension, right? I can take this part and I can turn it around, right? And I'm gonna push the string even more. I can also change the tension by pulling, right? Okay? I changing also the length and also the tension. That's what I'm doing. So so when I play chords, for example, we see guitar player playing chords. So I actually just changing the length. Like I play a lot of strings. When I sing, I'm changing the length of the string. Another cool thing, I can pull and change the tension of the string. Okay, so the string is like a spring. Okay, that's how I remember it. Okay, so I can change the tension. So guitar players change the length, and what's happening in piano? At the back of the piano, if you're gonna open the piano and pick up what's going on inside, so you're gonna see many strings. So the string already oriented, already stretch up, and you just need to play which string you want. In guitar, we have only 6 strings, but each time I modify the length of the string or the tension of the string that I want. Okay, and I have 6 different strings because I want to have many mus, okay? Many different kinds of material properties. And in piano I have a lot of string. Each key I think have 3 strings, okay? So that's the idea. So let's move on to the next part. So the next part is what is the hearing range of a human ear, okay? So let's clean the board. So what is your range, okay, of hearing? So in general, okay, people say that the human ear can, in the extremum, can hear from frequencies of 20 hertz till 20 kilohertz. Okay, let's do the 0, so it's gonna be more distinguished, okay? Kilohertz. So that's what you can hear, okay? But there's other animals, for example, elephant can hear 14 hertz. Let's do an elephant, small elephant. This is elephant, right? Cute elephant, happy elephant, right? So can hear even 40 hertz, which called infrasound, okay? And dogs can hear even greater frequencies. They can get to 60 kilohertz. This is insane. Dogs hear a different world, okay? A different world. They hear so much frequencies that we don't aware of. Okay, so this is dogs. Dogs. Here, dog. Also happy if the tongue outside. Okay, hear many frequencies. Okay, it's really sensitive. I put down in the details a really nice short video that you can check what is your limit. Okay, how much you can hear. So probably when you born you could hear this frequency, but right now, this frequency, but when times go by, you actually getting older. Yes, you are older, and that's the reason you actually can hear less frequencies. And all the sound that you go to the party and your ear are buzzing with pain, so this actually injure your hearing. So what I want you to do is go inside the link and let me know what is the limit, how old are you, okay, in terms of how good you can hear. Okay, enter the link and just see, it's a nice video, check yourself what is your frequency. I would like to see this in the comments. Let me know what is your range of hearing, okay, when you stop hearing I actually want to know when are you stop hearing the high notes. Okay, it's gonna be really high, you can skip to the end and just see, okay, I can barely hear it anymore, that's it. So see it in the comments, really interesting. Let's move on to the next question, which is relevant to this idea. So the question, this was just a warm-up to explain to you. So the real question is, what is the highest note? What is the highest note? Okay. We can hear from the string. Okay, this is the question too. So let's assume that you are perfect, okay, and you can hear this one. You are really a good child and you didn't go to a lot of parties and you didn't rule up your your hearing, and you don't need any hearing devices. Okay, you are a healthy, good person. So let's say that this is your maximum limit. Okay, so if that's the case, so we talked about that the frequency is actually to what? The frequency, the higher we can hear, high, let's do H, is, let's say it must be 20. Okay, so what is the mode that we are actually gonna hear? So the mode is N of the string, right? Of the string is multiplication of the fundamental one. So what is the highest mode? Note, sorry, not note. Let's do the highest mode or antinode that we can hear. Okay, so this multiplied by this. So N is approximately 101.81, and remember that N is a natural number. We're talking about the numbers of peaks that we're gonna see, right? So the peaks is actually 108.1. Okay, you can't have almost a peak. Okay, so it's not a peak. So this is the highest mode that you can hear from the guitar string. And let's do another question, really nice question. How the string gonna look like? Okay, how the string going to look like? So the concept here is that I'm gonna use lambda. Lambda is, the space orientation of the wave. So it's actually asking what is lambda. So lambda is equal to what? Lambda is equal to 2L over N, and we just found N, and L is given. So we're gonna get that lambda is 0.009 meter, which means it's 9 millimeter, which is almost 1 centimeter. So so what's the idea here? Is the idea that if you're gonna look at the string, if you're gonna take a really good slow motion device and look at the string, you're gonna see that the string of the guitar is looking like this. Okay, here it is. Like perfectly like this. Okay, each 1 centimeter you're gonna see peak. How many peaks do you gonna see? You're gonna see 181, including sorry, without this one. Okay, so that's what you're gonna see. Okay, every 1 centimeter you're gonna see this one. Okay, so that was the idea of the question. Perfect question. And we talked about the musical instruments, but I want to talk about something else. Okay, so the guitar is vibrating. This is super cool, this is nice, but the guitar is vibrating. I'm not connecting to the guitar. I'm not gonna hear the guitar. To hear the guitar, I need the movement of the guitar to hit the air and then to come to my ear. Okay, so we actually changing mediums. Okay, this is really important in waves. In waves, we're gonna change the mediums a lot of time. So let's talk about that. So if I wanna hear, okay, so let's change the question. So the disturbance of the wave, all the tutorial I was looking for the word disturbance. Okay, this is really important word. Disturbance, I don't know what's going on with me, but this is the word for saying that you have something that disturb the medium, and this one is propagating. Okay, that's a really key word in this subject. Okay, I want you to know that. Okay, so let's continue on. So right now the string is vibrating. Okay, we said in n equal 181, right? Lambda equals to we said 1 centimeter, 0.009 meters, right? We know the frequency, and the frequency was n multiplied by f1. F1 is 110, and n was 181, right? So this phenomena, and I'm here chilling out, you know, next to the fire camp, you know, having fun. My friend of mine playing the guitar, but this disturbance, here I have O2, right? N2 air. That's what you have in air. A lot of N2 and a little bit O2. Some molecule, you have molecules here, and this disturbance want to go and hit my eardrum, right? My diaphragm here inside my ear, so I can hear the guitar. So what's going to happen? I want to ask you, what is how it's going to look, the propagation inside the air? What is the wavelength of it? Okay, that's what I want to ask you. And so if I'm going to hit the air, okay, I'm the string, I'm vibrating, okay, and I slapping the air in this frequency. This is the frequency. It's really high frequency, okay? I'm slapping the air, okay? So what is the frequency which the air gonna move? The same frequency, okay? If I'm gonna slap somebody, okay, so his face gonna move like this, right? So it's the same frequency. So when you change mediums, okay, from my hand, slap your face and your face, okay, different mediums, they're gonna move in the same frequency. That's what I want you to know. So frequency is saved while changing mediums, okay? Mediums. That's what I want you to understand, okay? But what is changing? What is do change? So lambda is gonna change, okay? Think about yourself running, okay, in the medium of air, and then you going inside the water and continue running. It's gonna be, maybe you're gonna put the same frequency, the same the same times that you hit the floor with the legs, but it's to keep this space, it's gonna be really hard for you. Your distance you're gonna move gonna be smaller, okay? So that's the idea of lambda. Lambda is changing, okay? So this is lambda of the string, and this is the lambda of, okay, of L. It's different, okay? So let's talk about that. So what we can do, we can use the equation V equal lambda multiplied by F. So we talked about F. F does not change, okay? I'm gonna slap the air in the same frequency, which is this, 100 multiply 110, but I'm going to change my lambda. For what? I don't know. That's what we need to find. But I know something. We know how fast sounds go inside air. It's a known, it's like the speed of light. We know this term. Okay, so this term is equal to 330 meter per second. Okay, so this is the barrier of sound. This is the speed of sound. Okay, if I'm shouting at you and you 330 meters away from me, you're gonna hear it after 1 second. Okay, so this is the speed of sound. So I can, this is the reason actually I chose the note the note A, because it's 110. It's, look how beautifully it's canceling out. So this is 3 equal lambda 181. So lambda is actually equal to 0.016 meter. Okay. And another cool thing, okay, so we solved this. Another cool thing that you can do, you're watching me right now on YouTube, okay? Check down here, you can change the speed, right? Here, on here, I don't remember. Change the speed. What's happening? I'm talking to you. When I'm talking to you, I'm slapping the air, right? And it's coming through you in some frequency. For example, I'm talking to you. If you're gonna do it faster, I'm gonna talk faster. Okay, so you force me right now to slap the air into your ear in a faster rate. Okay, that's what's gonna happen. So this one gonna go up, this one gonna go down. That's what's gonna happen. That you're gonna enforce me to do that. So if this one go up, this is the frequency. I'm gonna sound like this. I'm gonna sound a little bit higher. And do the opposite. Put me on slow motion. Okay, I'm gonna sound a little bit lower, right? Because you take my frequency down. Okay, so this is really important. I want you to try this experiment at home. It's working beautifully fine because sound is wave phenomena. Okay, perfect. So we finish this question and moving to the next question, which is waves in a pool. Okay, so let's clean this board. Let's clean the board. You know what? I'm gonna do it in separate videos, so it's gonna be easier for you to distinguish between both of them. Okay, so I'm gonna see you in the next video going on. And if you like the video, comment below, like, subscribe to the channel. Also enjoy to do these videos for you. So make me know that everything is fine. Let me know if everything is okay. Tell me the frequency, which is your limit of the ear. It really interests me. So see you in the next video, which coming up soon.